Hi, in this video, we want to take a look at modeling aerial data. Now, specifically, we're going to be testing for spatial autocorrelation. Now, when I talk about autocorrelation, we're talking about regions this time. So we're not interested in individual points on the ground. We're talking about like neighborhoods, counties, states, census tracts, areas like that, areas that we represent with spatial polygons. All right, so that's what we mean when we say aerial. All right, so this is a little bit different because the normal way that we tackle autocorrelation really lends itself well to individual points on the ground. And so it's just very natural to take, basically modify the time series version to do spatial. Boom, we've got easy peasy, lemon squeezy. Here it's a little bit trickier because now with polygons, it's over an entire region, not just an individual points. So we're going to need to do two major things before we can get started. We're going to need to determine, all right, which regions, which polygons do we consider to be neighbors to each other? And after that, we need to consider weights between them. And the weight between non-neighbors is going to be 0. All right, so the examples that we're going to go through are from Applied Spatial Data Analysis with R, Chapter 9. Here are the authors. I've modified the code for this. And here is the book's website. And you can download this for free through UCF's library. All right, so let's get to the actual work that we're interested in. All right, so something that I need to emphasize is that our choices of how we determine neighbors and our choices for weights will have a huge impact on the output of our results. If I make a poor choice on neighbors or weights, it's going to be felt in the outcome. So when you make the decision, when you make those decisions on your neighbors and your weights in the previous video that I did, you need to really be mindful about what you're doing. Now, there are two types of spatial autocorrelation tests: global tests and local tests. Global tests, we're checking to see, is there spatial autocorrelation somewhere in this region? Yes or no. It doesn't tell me where. It just says yes or no. Do we have it somewhere? Local tests, what local tests are designed to do is to help us find clusters of neighbors with very different observations from their neighbors overall. And so what we think of it as, we're trying to find hotspots. And when I say hotspots, that could be with larger values or smaller values in the observed data. All right, so let's go ahead and talk about Moran's eye test. All right, so this is, from what I can tell, from looking through and reading, Moran's eye test is probably the most common way to tackle spatial autocorrelation. All right. And there's going to be some assumptions before we can get into this. So first and foremost, the mean model of the data removes systematic spatial patterning from the data. Now, something that will happen, and so is that if we're missing predictor variables in our model, this assumption will not hold. So this is one of those situations where I need to make sure I have all the data, all the predictors that are relevant to my situation. If, let's say that the data that is important just wasn't recorded, therefore it's not in my data set, then this assumption will not hold. Next assumption is that neighbors and weights, like the system that we have selected for neighbors and weights, reflect the autocorrelation relationship in the data. And so this assumption is that we made the correct choice on neighbors and weights. Now, there are residuals. So the residuals from the model, the distribution is going to have some assumptions. Specifically, we're going to be talking about the normal distribution. We'll also look at some bootstrap techniques that we can use to be a little bit more flexible. But whichever test I'm using, I'm going to have some kind of assumption on the distribution. And so, on the residuals, that is specifically the residuals, notice that we're not making assumptions about the distribution of the observed variables, nor are we talking about the distribution of the regions themselves in the study area. We're talking about the distribution of the residuals. All right, so Moran's I, this is how the author words it, which I'm going to articulate just to be consistent with the book, but it's calculated as a ratio of the product of variable of interest with the spatial lag with the cross product of the variable of interest and adjusted for the spatial weights. All right, so let's look at it a little bit differently. If I look here, that looks a lot like a weighted covariance. So I'm taking the weighted covariance of the observations with their neighbors. So realize that the weight is always 0 with non-neighbor entities. So here is like the covariance between observations and their neighbors, weighted. Here is the sum of squares deviation from the average. All right. Now over here, we're just rescaling things. All right, so I've got this n as a rescaling, and I'm divided by the sum of all the weights. So really, this is a good way to think about this, is that this is covariance between observations of their neighbors and divided by the sum of squared deviation from the overall average. All right. So centering on the mean, assume that the correct model has a constant mean. So when I'm doing my testing, as I go down the line down in this video, whenever I'm using a constant or a mean in the modeling part of the test, I'm making the assumption we have constant mean across the board. And under that assumption, any remaining pattern after centering is caused by spatial relationships encoded in the spatial weights. So this spatial relationships encoded in the spatial weights is why I have to get my weights so right, is why it's so important. Now, under the mean centered assumption going on, the expected value of I is -1 over n minus 1. All right, so now let's actually get into R and run Moran's I for spatial autocorrelation. So we're going to use spatial weight matrix in its weight list form. So that's from the previous video. So remember that we had weight matrices and we also had list W objects. Now, the assumptions of the underlying test are sensitive to the form of the neighbor relationships. And so that's important. Now, something we can do to check is that we can use this permutation function to check to see if our assumptions of the neighbors are correct. You know, as I run through all of the different examples, notice how the p-value changes with different neighbor weight relationships. All right, so on this first example, I've just got random data, and fortunately, we're going to see no trace of spatial dependence. You'll notice a p-value of 0.7. All right, so when we run this, what is spit out on the surface of Moran's I test, we have our standard deviation of -0.4. We have the I statistic of negative 0.5. We have what the expectation would be. So under the null hypothesis, we're saying no spatial autocorrelation anywhere. And then here is the variance. And so many of the tests, how they actually get the p-value is they take the statistic minus expectation, divide by the square root of the variance estimate. Standard way, and then compare to the normal distribution. That is by far the most common approach frankly in statistics. And so we're making the assumption that things are asymptotically normal. We'll also look at bootstrap approaches in a little bit. All right, so let's go ahead and take the spatially autocorrelated variable that was built in the previous video. So I call it autocorrelation of random norm. So it was originally random norm data, and that was converted into autocorrelated. All right, so here our standard deviate is 2. Our p-value is 0.04, statistically significant at the 0.05 level. Here, I see my test statistic. Here is the expected value under the null hypothesis, and here is the variance estimate under the null hypothesis. All right. And so now here I'm running the same tests, but this time, so here, let's show the difference. Here is my list W. Now this list W is I'm taking the NB weights, I'm taking the neighbors for Syracuse, and I'm doing row standardization of the weights. Let's see what happens. Well, you notice that I get the same p-value, the same standard deviate, and I get the same values for that. Now here, this neighbors came about from k nearest neighbors with one neighbor. So this is in a situation that each region has one neighbor and it is their closest neighbor, and that's it. All right, well, let's see how the model or how the test changes. All right, well, you'll notice that now the p-value is 0.006. It's dropped. Here's a standard deviate of 3, which is bigger. We have a bigger test statistic. We have same expectation and smaller variance. Actually, no, yeah, larger variance. Now let's look at the same one, but when I ran with 2 for my k nearest neighbor algorithm. Once again, relatively small p-value. Now let's look at when we ran for 4 nearest neighbors. All right, so that is several ways just to run the test where we're taking that constant mean assumption. Now, what we could do, if I wanted to, I could actually include a trend in the data going from west to east. All right, so here, this part of the code is just saying how far from the west boundary are we? And then I'm creating a linear equation where how far from the west boundary is multiplied by this relatively small number. And then I'm dropping that into the data. And so this gives me an easy way to tackle a trend going from west to east. And so we see that it's not statistically significant, well, which is good because here the baseline was just random noise. Something that is also very nice is that we could actually pull in a linear model. So if I had data and I had predictor variables, I can put it into the LM is for a linear model, lm.Moran tests, and the model part takes care of it. Now you'll notice that I still need my neighbors, I still need my weights to run this. Now, if you look at this, you'll notice that it's a little bit different. Why is it different than what I have here? Here, I've already specified what the coefficient is. Here is trying to get the best fit it possibly can. If it's getting the best fit it possibly can, it's going to account for as much variance as possible, which means there isn't going to be a spatial pattern left to be detected. And so the p-value is larger. So in this situation, we're more prone to conclude that there's no spatial autocorrelation because we're working on the residuals. So if I have a model that, if I put a model inside that accounts for more of what's going on using predictor variables rather than spatial aspects, my spatial test is less likely to reject the null hypothesis. All right, so let's go ahead and let's do our global tests. All right. In this video, we're going to stop at global tests. We're not going to go into local. Local will be the next one. All right, so for this situation, our null hypothesis is that there is no spatial dependence for the chosen spatial weights anywhere in our study region. The alternative is that there is spatial correlation somewhere in there. All right, so parametric tests use that normal distribution where we take the difference from the expected value divided by the square root of the variance. So, the very standard, very common, that's how we do it in statistics over and over and over. Now, something that is important about this is that that variance calculation uses the weights in that calculation. So once again, we see that if I made a poor choice on my neighbor and weights, I'm gonna feel it down the road. Now, the bootstrap techniques, what they're going to do is that they're going to take all of the observed values over all of the different polygons that we have, and they're going to permute them around all over. They're going to randomly switch and then compute. Randomly switch, compute, randomly switch, compute. Do this, 10,000 times, we'll get a distribution for the test statistic. Then we take our original data test statistic, compare it to the permutation distribution. Now, something that is important about this is that the SP-DEP package does not want to see empty regions in terms of neighbors. So we want to see that every single region has a neighbor. In our neighbor scheme, we don't necessarily have to do that. An example of this would be if we're talking about states in the United States, we could say that Hawaii and Alaska do not have neighbors. That makes sense geographically, but for the purpose of running autocorrelation tests, those are problematic. The entire system for running spatial autocorrelation was built up under the assumption that every region has at least one neighbor. Okay, so if I do have 0 neighbor regions, what I could do is I could say 0 policy equals true to allow the computation to happen. Now, leaving that as is, we will likely see an inflation on our test statistics. I can do adjust.in to help prevent that inflation, but still, even under those considerations, those adjustments, I really would be better off with the situation of having everybody with neighbor, even if I have to exclude some regions from my data. All right, so here, this is Moran's eye. Here it is, the covariance divide. So this is the presentation that is in the help documentation in R. The previous formula we looked at is from the textbook itself. And so we see that it's autocorrelation between points, or not correlation, covariance, divided by the sum of squares, deviation, multiplied by n, and this is going to be the sum of weights. All right, so now let's go ahead and compute. So here, I'm just running Moran's function on the cases of leukemia in the Syracuse area for the data set we have. I'm using the New York neighbors data set, and we're going to go ahead and say that we want binary, so that if they're adjacent to each other, they're neighbors. If they're not adjacent to each other, they're not neighbors, and we have a weights of 0s or 1s. And so here, we're just going by the number of cases, and this is determining the weight aspect, that S0. So that rescaling, and we can see that here is our I, and here is the K value for this. So in the cases data, that's the number of cases of leukemia in each of the regions. Now, in the data buildup, it worked out that there were there were known cases of leukemia, but it was known to the researchers that cases were in, let's say, 1 of 5 different regions. And so in that case, that one individual with leukemia would be would be count-wise distributed over the 5 different regions to be like averaged out, because there wasn't that as refined of a data set as they would have liked. And so when you look at the actual cases in the data, they should be counts, but they're not counts because of they distributed individual counts over the region. It was the regions it was known to be in, but they didn't know which specific region it was in. All right, so for Moran tests, here I'm taking the cases of leukemia, and here I'm making my weights for the New York neighbors. And here we can see that our p-value is statistically significant. Standard deviation is 4. Here is my expected value. Here's my actual statistic. And here is the variance using the data and the weights to compute that. All right, so let's go ahead and test for spatial autocorrelation using binary weights. So here I am constructing, binary weights, and I'm dropping this in. You'll notice that, let's look at the difference between these. So both of these have the cases going as the same. Here, I'm using default settings to set up the neighbor. So here, this is using row standardization. W is the default parameter value for the style. Here, we're using binary. So up here in this one, we're using weighted average. Here, every neighbor gets the same amount of influence. And so here we see a slightly different p-value. All right, so the Moran test uses randomization assumption, which differs from regular normality by introducing a correction term based on the kurtosis of the target variable. Now, if the kurtosis is equal to that of the normal distribution, the two assumptions yield the same variance, and so we'll get the same results. But as the variables depart, the kurtosis departs from normal kurtosis, then we'll see that randomization assumption compensates by increasing the variance, and we'll see like a split in the value that we get in our conclusions and our results. All right, so here, let's go ahead and put randomization equal to false. And so now I'm going to be using the assumption of normality in my calculation. And so here we see, honestly, in a lot of these, we're seeing like the same p-values, or practically the same p-value over and over and over. And the author of the textbook talks about how operationally it doesn't really matter that much which one you pick, but if you have subject matter knowledge of what's going on, go with that. If your client wants something in particular, go with that. If you don't know, run the defaults. There's a reason why the author of the package picked those defaults. All right, so now let's go ahead and see what happens when I go with a linear model of cases belonging on being dependent on a constant value. So here, this is going to be a constant mean across all regions, and we're going to run autocorrelation on the residuals, that is the deviance from the mean. And you'll notice that once again, I get 0.007. Notice I got 1104. 1104. You notice that here, it's a 3.6 and 1.3. 3.6 and 1.3. 3.6 and 1.3. So slight variations are giving me the same results. So in fact, the linear model with just the intercept is actually the same as running just on using the mean assumption. Now, there are other ways to get the distribution. So, when I'm doing the normal assumption, I'm making a pretty big assumption, and there could be some problems with that. We could use a saddle point approximation of the distribution using a method of moments. And so this is similar to, this really is like a numerical analysis approach to approximating the distribution. And so here, if I do linear model, Moran test, and then dot saddle, then I can see the results. Now, this is going to take a long time to compute if I have a large data set. And so this may not be feasible depending on what you're doing. And the increase in a more precise distribution may not be worth it. Now, here is an exact test. So exact tests are usually preferred, but once again, this could be computationally not feasible for a larger data set, and the amount of improvement may not be worth it. Now, we could also use a Monte Carlo approach by going through, and I'm going to permute the location of my observed value. So I'm going to randomly shuffle up where each observation is coming from, and then I'm going to run my test statistic. I'm going to do that over and over and over, maybe 10,000 times. That's going to give me an empirical distribution, and I can use my original data, compare the original data results to the permuted version distribution to get a Bootstrap hypothesis test. And to do that, we do Moran MC, Monte Carlo, and here we get our p-value. All right, so now let's go ahead and let's make the assumption that we have constant rate across the entire study region. And if we have that assumption, then let's go ahead and compute what that is. Well, that's going to be the sum of cases divided by the total population. And so that is our average rate of cases across the entire study region. Now, what I want to do, I want to see under that assumption, how many cases of leukemia should I have in each of these regions? Well, I'm going to take the rate of cases, and I'm going to multiply by the population in each region. Boom, I've got the expected value for each region. All right, so now here are some functions that we're going to do. So we're dealing with counts, so I'm definitely going to be using the Poisson distribution. So CR is a random number generator. And then here, Moran IP boot is I'm doing the Moran test. And then I'm grabbing the I statistic. So I'm just grabbing the I part. I'm going to set the seed. And so now I'm going to use the boot function from the boot package to do bootstrap calculations. And so here's my data. There are my cases. I'm going to drop things into this function. I'm going to do just under 1,000 simulations. We're going to do parametric simulations on this run. Here is my random number generator. Here are my weights. Here's the n. Here's that rescaling aspect for the I, and the expected cases gives me my maximum likelihood estimates. So the MLE is used in that random number generation. So now let's go ahead, after I compute this. So here, this will give me the Bootstrap output. Let's get the p-value from a Bootstrap one-sided normal test. So T sub 0 is the observed Moran I statistic from the original data, and T are the Bootstrap Moran I statistics. All right, so here, boot cases, T sub 0, that is from the original data. Here I'm taking the Bootstrap generated values, the average of them, and then here is the standard deviation. And so now I can get a one-tailed test using p-norm, and I'm getting the right side because lower tail equals false. So we see it's not statistically significant. So now let's go ahead and visualize the results of the permutation bootstrap and the parametric bootstrap. And so all of this is just setting up the plotting region. Here is the histogram of the permutation bootstrap. Here I'm going to have my test statistic. And now here I'm putting 2 on there. I'm going to have here we go. It's just show it. All right, so here is my permutation bootstrap results. So that's pretty far to the right. Here's the parametric bootstrap results. All right, so I've got 2 bootstrap ways to approach this. And you'll notice I'll reach different conclusions. Here's the parametric one where I subtract the mean, divide by the standard deviation. Here's the one from using the bootstrap results themselves. So I'll reach different conclusions. Now we can also tackle the same problem by saying that we have the log of the population with an offset value. So the offset means that we specify what the coefficient is in the equation in here. And then the intercept is being fitted, is what this is saying. And we can do a generalized linear model to do exactly the same thing. I didn't give the outputs on here. Oh yeah, so it ends up that this intercept is negative 7.49. I ran the code early. I went ahead and put the convergent starting value just to make the code faster for the purpose of making the video. But it ends up that the formula here, cases, is going to be equal to negative 0.49 plus the log of the population under that model. Now, something that can happen when we have areas of low population, we can end up getting extreme rates just because we don't have enough of a population for things to converge. This is especially true for rare values. So if I have rare diseases, a region with a small population, one observation can skyrocket the observed rate. Now, also on the flip side, from a small population, if I just happen to not see the disease, just because it's a small population, that can make the rate look very, very low. Okay, so something that will happen is that low population areas, the rate is statistically not consistent with everything else. How could we handle that? Well, empirical Bayes gives us a way to tackle this. What empirical Bayes will do, if it's a very extreme value, so maybe just a few rare disease cases in a small population, will look super high for the rate, but we know from looking overall that's not realistic. So let's pull that down a little bit. Or if it's super low, let's say like it's 0, let's go ahead and pull that up towards the middle. That way, we don't have such extreme values pulling our model away when we know that the small population really is to blame for the extreme values. And to do that, we just do empirical Bayes I Moran. It's a permutation method, and it will knock this out for us easy peasy lemon squeezy. And so here we have a p-value of 0.03. Now, something I could also consider is higher order neighbors. So in this situation, let's say I'm interested in running neighbors. Well, we could say that, if we're talking about Florida, Florida borders Alabama, Alabama borders Mississippi, but Mississippi does not border Florida. But Mississippi is a second-degree neighbor of Florida. All right, well, so in that situation, maybe if we're in a situation where we want higher order neighbors, let's say that, okay, we want to, if it's a neighbor of a neighbor, I want it to be included in the calculation. Or maybe a neighbor of a neighbor of a neighbor could be counted in a calculation. All right, so we have that option with the neighbor lag function. So here, neighbor lag of 2 says we want second order. Now, what this will do is this will create a list of neighbors, and it'll be a little more complicated of an object. And this will create a cumulative neighbor object overall if I want to pull in second or third or fourth degree neighbors. Now, when we look at the correlogram from the SP-DEP package, so I'm taking my neighbors, taking the variable of interest, I'm going order 8 because I'm just exploring. Moran's I, and here is how we're setting up, the weights of C. Here we can see that in this situation, it looks like degree 2 neighbors should be considered, but degree 3 should not. And so once I hit no for something, I ignore the rest. So once I see it 3 is not statistically significant, I'm not worrying about anything below. So everything we've done so far is that we are interested in first degree neighbors, immediate neighbors. If I want to go 2 out, so this would make sense if I had very small neighborhoods, right, where there isn't much geographic difference between second degree neighbors. So now let's go ahead and use the p-gearmess correlolog function to visualize. Here I'm specifying what the coordinates are. So I'm extracting the coordinates from the spatial data frame object. I'm specifying what the values are for each region. And I'm saying Moran. So here are the core log cases. Notice that we are statistically significant at 2, but not 3. And when I visualize this, I just drop each of these into plot. I can see that order 2 neighbors would be something I would want to definitely look into. Now we have alternative ways to tackle this. There's Gary's C-test for spatial autocorrelation. And once again, this is sensitive to the form of the graph of the neighbor relationships. And we can use Gary MC permutations to check to see if our assumptions are reasonable. And there's the global G test. Now here, it requires that the data has to be positive data, and it works better when the weights are binary. And so here you'll notice that I added a 5 to the data just so that it would run. And so these are alternatives if you don't want to use Moran's I. Here's another alternative that uses Mantel, Hubert, cross product statistic. And so here we've got a lot of stuff going on. We've got Moran, Geary, and Sokal. And I can get the test. And we can, so what I like about this more than anything is that it's easy to plot and see what's going on visually. All right, so now with categorical data, if I represent it as factors, we have some tests that we can use. This package is SPDEF package is nowhere near as deep into factors as numeric values. So let's say here, I'm just going to go through and I'm going to convert that autocorrelation data that we had from the previous video. I'm going to convert it into greater than median, less than median. Or this actually should be less than or equal to, but I kept it simple. And so here we can do join count statistics for the K-colored factors. So this is join count.test. Give me this result. And we use a permutation test for same color joint count statistics. And so here, I'm just dropping this in, joint count Monte Carlo. And I can see my p-value. And here is another one, joint count multi. And so these are all tools if I need to work with factors. These are available to us. The textbook doesn't talk about them too much, so I'm just going to leave them. If you need to use those in your own research, they're in the package and the help documentation is there. Well, that's all I've got for you. Take care and goodbye.